and then I will give everyone some cues. Because it says live, but I'm not entirely certain. But I just want to give you both a heads up that here we go. Yeah, so we are actually live at this point. Let me just sort of thank everyone who's actually joining us online. At the moment, you can see essentially my screen. My name is Martin Peacock. On the call today, we also have several colleagues. Also, we have Professor Hemantejad, and I apologize for my pronunciation, but we also have Ali on the line, and we also have Solrun from Norway. So I think you've got two people in Iran, two group people in Norway, and one person in the UK. So it's very kind of, let's say, international this afternoon. So what I want to do then is, Ali, if you want to introduce our guest, and maybe we can have a kind of quick introduction from our guest about this afternoon.
Yeah, sure. So actually, I just want to give a quick introduction in Persian because some people are from Iran. So I just want to give a quick introduction in Persian. سلام عرض میکنم، عرض خیر مقدم دارم خدمت همه دانشجوها، محققین و حالا اساتیدی که زحمت کشیدن تشریف آوردن. وبیناری که امروز ما در حال برگزاری هستیم در واقع بین دانشگاه شیراز و شرکت زیمر اند پیکاک هست. شرکت زیمر اند پیکاک در واقع یک شرکت توی حوزه تکنولوژی هست که تولید کننده سنسور و بایوسنسورهای الکتروشیمیایی هست. البته یه سری اکسسوری‌های الکتروشیمی و تجهیزات الکتروشیمی مثل پتانسیومتر و رفرنس الکترود اینها رو هم تولید میکنه. حالا خود آقای مارتین پیکاک توضیحات لازم رو میدن. راجع به آقای مارتین پیکاک هم من بگم که ایشون در واقع جزء پایه‌گذارها و کوفاندر شرکت زیمر اند پیکاک هستن و در واقع خودشون هم تخصصشون الکتروشیمیه، یعنی دکترای الکتروشیمی دارن و میشه گفت که یه جورایی مسئول بخش تحقیقاتی شرکت هم ایشون هستن. عرض به خدمتتون که حالا دانشگاه شیراز هم که خب فکر کنم آقای دکتر همتی نژاد زحمت بکشن یه توضیح میخواید بدید راجع به دانشگاه.
Okay. Yes. Hello, everybody. My name is Bahram Hemmatinejad from Shiraz University. Welcome to this talk. And I actually would like to thank Ali Aqai and Dr. Peacock, if I pronounce it correctly, that organized this seminar. So it is a great pleasure for us to host this seminar in Shiraz University from virtual mode. Okay, so I try to introduce Shiraz University shortly. Shiraz University is among top 13 universities in Iran. So it is a comprehensive university. It offers almost all programs in science, social science, engineering, veterinary, agriculture, and so on. So there are 18,000 students in this university, about 18,750 professors or academic staff, and about 1,200 non-academic staff. Chemistry department is one of the oldest department in Shiraz University, and so it's a pioneer chemistry department in Iran. So the first PhD program in Iran was started by this department in Shiraz, and this department ran 5 programs in one program in bachelor, 5 programs in master, and 4 programs in PhD. In bachelor degree, in undergraduate, we just offer pure chemistry, but in master, we offer analytical chemistry, physical chemistry, organic chemistry, inorganic chemistry, and polymer chemistry. And in PhD, we offer analytical chemistry, physical chemistry, inorganic chemistry, and organic chemistry. So polymer chemistry, rather now in this department. This department is composed of around 25 academic members and about 200 graduate and 200 undergraduate, roughly equal number of students in undergraduate and graduate programs. So in analytical chemistry department of this analytical chemistry group of this department, we are 5 professors working on different branches of chemistry, mainly focused on sensors, electrochemical sensors and optical sensors. And in my research group, we are working on optical sensors, and my interest is paper-based analytical devices. So we work on paper microfluidics and paper-based sensor arrays. Okay, and so for arrays, you know, we need some computational and analytical data analysis methods. So in Iran, I'm famous for chemometrics, not for sensors. But I would like to apply chemometrics on sensor arrays. Okay, so we process the data collected from sensor arrays and use some multivariate data analysis to extract patterns, and so to extract some useful information, make some multivariate calibration, multi-component analysis, and so on. Okay. So.
Actually, before we start, I was trying.
Yes?
I was trying to get Dr. Yamini into the webinar, and he's saying he's not able to get through. So, can we check with someone in Iran if they have entered the room?
Just for your interest, we do have delegates
because
online.
There are 2 links.
Yeah. So the delegates are online. So I think we should definitely sort of carry on now with them. So we've got a good turnout of delegates online. So I'm thinking now we've had a. If I look at the agenda, we haven't really given a quick introduction to ZP, but we have had an introduction from Shiraz University, and I thought that your comments on paper-based microfluidics were very interesting. It's a little bit unusual, but we've got a couple of colleagues from Norway on the line this afternoon. So what I'm going to do is I'm just going to stop sharing my screen and mute myself, and then my colleagues from Norway will just do a quick demonstration about measuring nitrate. So one of the kind of interesting analytes for the future in biosensing is going to be agriculture. I know people are interested in pesticides. So brilliant. So this is my colleague, Solron. If you want to go ahead, Solron, that would be fantastic.
Yeah. Hello. Welcome to ZP in Norway. My name is Matthew, and I'm here with Solon, and we're going to just run through a quick demonstration on how to do a test of nitrate solution on our nitrate sensors, which are primarily used in agricultural applications. So I'll pass over to Solon, and she'll take us through what she's going to do.
Yeah, so here we have Zimmer and Peacock's nitrate sensors. So we'll insert that into an anapod like this. And then here I have 3 different concentrations of potassium nitrate that I will apply each in turn. And I will soon be sharing my screen, and then you won't be able to see what I'm doing. But basically, I'm just wiping off the solution while applying a new concentration. So I'll start sharing my screen now, and then hit share. And we have a bug. Perfect. Close the program. Okay, but you can still see me, hear me though. So I'll just continue then. I'll start the program, and while it's running for a few seconds, I
That's a bit of a shame because you were definitely sharing your screen earlier on.
Yeah, I was, but it got disconnected. So, but give me 10 seconds and I'll be there.
I see. So you've had to come back into the program, is it?
It's the wrong VMware.
Oh, shoot. Cancel and go to Martin. And while I'm doing this, it's running. It's doing an open circuit potentiometry. So basically what it's doing.
Yeah, we see it. We see your camera now. So you've come in on your camera. So just share that screen now.
So basically what it's doing is that it's testing the potential between the reference electrode and the working electrode. So we'll pause the recording for now, and then we will wipe off the solution. We'll add a new solution of higher concentration. So now we're on 3 millimolars of potassium nitrate, and I'm using 60 microliters because by experience that's perfect. Then I'll hit play again, and now you see that the potential is lower now that we've changed the concentration. And yet again, we will pause it. We will swap the solution with even higher concentration, and we now expect it to run even lower on potential. So we'll see if we know what we're doing. And then we'll hit play.
No,
and here's another step for you.
I mean, it's very. I mean, what you're doing here is you're basically got an ion selective electrode. So you've got a small potentiostat, a nitrate sensor, and a series of nitrate solutions. And when you look at this, you've got perfect staircases as the voltage is changing. As you, keep that screen on. As you change concentration, we're obviously dropping. Well, the voltage is changing as you change the nitrate concentration. So I mean, what's really impressive about that is I'm actually a little bit surprised how stable the signal is. Then you change the concentration, and then the signal changes, and then you change the concentration, and then the signal changes. So I think that's really quite good work. So what I want to do then is I want to thank. So we did that slightly unusually. So we did the demonstration first, and then in a bit we'll actually talk about the theory a little bit more. So let me just say thank you to my colleagues, and then I will share the screen. It's always interesting trying to do live demonstrations, but I thank you for that because obviously you made it work in real time, and you had more problems with the video conferencing system than you did with the actual experiment. So thank you for doing that, guys. So what I will do now is hopefully my screen is sharing. Yeah, there it goes. Okay, cool. Right, so we did a quick demonstration. Now let me just sort of back up a little bit now and say, look, I appreciate that we've been invited this afternoon to speak by Shiraz University, and I thank you all for essentially coming along. Just very quickly, Zimmer and Peacock, we're an electrochemical business. We're very interested in microfluidics, even paper microfluidics with waxes and things like that are very interesting to us. We're located in the US, UK, Norway, and France. We do a lot of biosensor development, biosensor manufacturing, and microfluidics because microfluidics and biosensors go together. Microfluidics brings the sample to the sensor, and the sensor analyzes the sample. So we're very keen in both those aspects. I won't talk a lot about myself, but some things that might be interesting is we have very good ties with the University of Oxford in the UK, and we're also tied to quite a few universities, let's say in general, in Norway. Just to give you a quick sense of us, if you ever visit our facility, we've got really state-of-the-art facilities in terms of potentiostats, biological facilities, microfluidic facilities in terms of engineering facilities. So we're very well equipped. Today, the company is a company of 85 people. And we have both manufacturing centers and also R&D centers. I think what makes us unusual is we have quite a young company, and we're very diverse. In total, there's about 27 languages spoken within the business. And I think, it's fair to say it's quite a happy company, that we we embrace our differences, and we're really, we have a nice culture in the business. The reason I was kind of keen to start talking to, the universities across the world is we're very good at supporting projects. So, we support undergraduate and master's projects. So this year we've been supporting projects that were just IT based. We've been doing projects where we're supporting the development of implantable sensors for fish health. We've been doing projects where we've been looking at immunosensors for looking at protein detection. And this is another one. That one was for fructose, and we've also been doing immunosensors. So what this says is, and the reason I was kind of keen to have this joint webinar this afternoon is we're very keen on collaboration at Zimmer and Peacock, and we will support projects across the globe with our technology and with our help and with our advice. If you're not sure about biosensors, we do have a few free modules online. We have something called the ZP Academy, which you can find free information, you can enroll, and you can learn about electrochemical biosensing. And we also have something called the ZP Developer Zone, where we do a webinar every week about biosensing, and it does include microfluidics on occasions as well. Now, this webinar is really about modern biosensing. So I think something that's really impacting biosensing these days is the Internet of Things. The Internet of Things is this idea that all devices are connected to the internet. And the reason that this is now possible is because electronics has got so sophisticated. Electronics could be low power, they could be miniaturized. We've got fairly good connectivity. We can connect things to the internet. We do have cloud computing, and this is a technology that we have in-house. What's really changing these days is we have data science and AI. I mean, anyone who's listening to today and you're an undergraduate or graduate and you haven't started to learn Python or coding, I would suggest you did start to learn it. For guys like me, it's I'm not saying it's too late, but I would say, but if I was starting my career now and you're doing chemistry, analytical chemistry, also start learning coding as well. And something that's really important to the future of biosensing and modern biosensing is smartphones. These smartphones give us the connectivity. They allow us to develop apps. So they're really important for the future of biosensing. So as I say, there's the Internet of Things where people are going to connect devices to the internet. But for us at ZP, what's missing is the chemical and biological sensors. You will find smart devices where they're measuring temperature, humidity, and pressure, or light. These are quite easy to do. But you will find that actually there's not sensors that can measure pesticides or the quality of water or the amount of bacteria in devices. And so for us at Zimmer and Peacock, the Internet of Things revolution is here, but actually there's a big gap in it, which is there aren't decent chemical and biochemical and biological sensors. So at Zimmer and Peacock, we know that, there's all these smart devices. I have a Google, device at home. I have an Apple Watch on, and all these things connect to the cloud, and we call that, IoT, the Internet of Things. But for us, all these devices are smart, but they can't tell you about your body. I know that you can argue that the Apple Watch does have a couple of LEDs on it, and those LEDs can start telling you about pulse rate and heart rate maybe, but they can't tell you about the glucose in your body, or they can't tell you about the lactate in your body. So we're starting to, at ZP, we think these devices are all smart, but they can't tell you about yourself. They can't tell you about farming or, how much nitrate is in the soil. They can't tell you about the water quality, and they can't tell you about the environment. So for us, the Internet of Things revolution is really important to biosensing, but biosensing is really important to the Internet of Things because it provides the smart edge between us as human beings with all our biology, chemistry, and biochemistry, and the biosensors connect us essentially to the cloud. Now I'm going to slightly change course. Now, Solrun, this video will also be on YouTube afterwards. If you watch that video, she did a series of concentration changes, and the voltage changed. Now, what she was actually doing was testing a nitrate sensor with known nitrate concentrations. So those nitrate sensors, if you look back at the video, you'll see that we had voltage versus time. And that's because we were using an iron selective electrode. And you're not sure about iron selective electrodes, then look at those ZP Academy courses that I mentioned earlier on. So the most, let's say, ubiquitous or common ion selective electrode is the pH sensor. Ali's online with us this afternoon. I think part of Ali's background is he's a very strong analytical chemist. So he'll know that every time you make a solution, you do something in the lab, you often make a pH measurement. And it's worth saying that those pH sensors are potentiometric or ion selective electrodes. And the nitrate sensor that Solron was demonstrating was also an example of an ion selective electrode. Just for your interest, an ion selective electrode, this is the electrochemistry part. It has two electrodes, one of which is the ion-specific electrode and one of which is the reference electrode. And we measure the voltage between them. So it's quite simple. It's just a measurement of voltage. But the idea is that the voltage of the nitrate is proportional to the nitrate concentration in the case of a nitrate sensor, or it's proportional to the pH in the case of a pH sensor. So I'm just showing you some raw data here. Now, this raw data is similar to what Solron was doing. So Solron was doing a live demonstration. And I think in some ways that gives you a lot of understanding of what a powerful science electrochemistry is, because they did that demonstration quite quickly and it worked. And the only problem they had was actually with the video system. So it tells you sometimes electrochemistry is quite a robust science because it's harder to set up the video conferencing than it is to actually do an electrochemical experiment. But what she showed you was she started off with a low concentration of nitrate and she increased the nitrate concentration and the voltage actually was going downwards. It was inverse, but that's okay. So here in this data, we show voltage at high concentration, a voltage at lower concentration, and a voltage at an even lower concentration. And you can see here that we're changing it by a factor of 10. And I didn't mention it, but there's an equation that governs all of this. It's called the Nernst equation. And it says that the voltage is proportional to the log of concentration. So if you want to see a decent signal, that's why we go from 30 to 3, because that's a 10x change, and therefore we can get a good signal out of it. So let's talk about, we showed you a demonstration on a nitrate sensor, and we're here to talk about modern, let's say, biosensing. And for me, modern biosensing is really helping the Internet of Things. And the Internet of Things is about putting sensors in the environment. It could be water sensing, or it could be putting sensors in the soil and measuring the nitrate in the soil. So just to give you an idea, the sensor that Solron was testing was a little device. It was quite small. It was 25 millimeters long and 7 millimeters wide. But that sensor, we've been developing it now. So we've been putting it in housing to make it robust. And we've also been turning it into, let's say, a real product. So we've been working on making these nitrate sensors implantable in the soil. So we did the demos. I'm not going to do the demo, but I am going to talk about the application of nitrate sensors. So first of all, the problem that we're trying to solve. The problem that we're trying to solve is, doesn't matter where you are in the world, if you're in Iran, if you're in the USA, if you're in Europe, if you're in Africa, people are unfortunately putting fertilizers onto the fields. And just out of interest, the fertilizer production in the world accounts for 1.2% of the carbon dioxide production. So if you want to reduce CO2 reductions by just 1%, which is not that much on a global perspective, then actually reducing fertilizer production is a good start. And 1% of the power that the world consumes, it goes into fertilizer production. So there's a global concern with nitrate production. But what the farmers are doing is this. They're putting nitrate on the field. They want it to go into the plants. But unfortunately, it's leaching off the fields into the rivers and causing algae bloom and pollution. Or it's actually leaching into the aquifer and polluting the water, which can then cause problems with the purity of water. So at ZP, we're trying to develop a technology that goes into the soil, constantly monitors the nitrate, and transmits the data to the smartphone. That's really the Internet of Things. Like I say, I want to introduce the Internet of Things concept because actually we're applying it very much to the nitrate sensor. So just to give you an idea, Zimmer and Peacock, we're quite unusual that We collaborate a lot with academia. So this is Dr. Tony Miller, or Professor Tony Miller at the John Innes Centre in the UK. And he first developed these sensors, and this is his prototypes. And what we've been doing is turning his prototypes then into much more of a product. And this is sort of essentially the modules that we now produce. But these modules fit on these rods. What's really hard in science is to take science out of the lab and put it into the environment. So these pictures I'm showing you now are us taking these electrochemical ion selective electrodes and putting them into the soil. So literally we are putting them into the field. So just to give you a sense of where these are sitting. And so these sensors now are sitting in fields in the UK, and we're monitoring the nitrate in the field. So what I'm about to show you is very modern, because this is a modern application of biosensing that really wasn't possible 5 and definitely not 10 years ago. It's only possible now because we have things like LoRaWAN, which is is a network that we can connect to. It's possible because we do have fairly decent solar panels and we do have decent electronics. So in this application, what's happening here is this. The farmer applies fertilizer to the field on the 30th of March. Now, at this point, he's watching the nitrate, so we can see the data in real time. Now, what happens is this. The nitrate starts going down. So the farmer has applied nitrate, but he has not seen the benefit of it. In fact, the nitrate is going down. And the reason the nitrate is going down is because the ground is drying out. So as the ground dries out, the available nitrate goes down because the nitrate is not solubilized. But the farmer has no indication that this is the case. No idea, because he has he doesn't, before he had these sensors, he wouldn't know about the real nitrate. He would only be guessing and estimating. Now what happens is this, it rains. And when it rains, the nitrate shoots up because the rain comes down, the nitrate, which is inorganic, dissolves, it solubilizes, it runs to the nitrate sensors, and we see the available nitrate shoot up. And that nitrate keeps on shooting up. Now, what happens here is it rains again. So now it's rained once, now it's raining twice, and the nitrate is going up. And in fact, what's happening is he's adding more fertilizer. So he's added fertilizer, the ground dried out, it rained, the nitrate shot up. But before he'd really seen the benefit of it, he added more nitrate, and it shot up even more so. So it's all the time it's raining. And then the farmer added another dose of nitrate, but it stopped raining, and the apparent nitrate went down because the ground was drying out. And he only saw the benefit of his last dose of nitrate several days later when it rained again. So the story is here. I was speaking very quickly because I'm conscious of time, and being very efficient with all your time, but the story is here. 1.2% of the carbon dioxide that goes into the atmosphere every year comes from nitrate production. 1% of the total global power goes into nitrate production. People think that 2/3 of the nitrates that are added to the fields are wasted, but they only think this. They have no direct data. But this data tells you exactly that conclusion is exactly correct. So it tells you that you could reduce 0.8% of the global CO2 just by cutting the nitrate production by 2/3, and this data would support that actually you could do that. Now, for us, the farmer is interested in the environment, but of course, what he's really interested in is saving money. So this would save him 2/3 of his money that he's otherwise wasting. And I know Ali has an interest in water quality. So the question is, where did all the excess nitrate go? It went into the water course. It's gone. It's gone into forming local pollution. So not a good outcome. So that is modern electrochemistry, putting sensors in the soil, getting real-time data so that farmers and agronomists can make decisions. And just for your interest, we are making these nitrate sensors available. So if you know people who are interested in having these sensors, they are free, and people just have to sign up to be a beta tester. The reason it's free is the UK government's been so generous to support this science and technology. So I talked very fast. I was extremely happy to be invited here this afternoon and to have an opportunity to speak to you all directly. Let me just sort of say a few things. the future for us all is the Internet of Things. You know, the Internet exists, but the Internet does not interact with human beings because we are biochemistry. The Internet can't tell us something about soil. It can't tell us about water quality. It can't tell us about the environment. But if you're hearing this talk today and you're interested in biosensing, biosensors are the smart interface between the Internet and the world that we really live in. And one of the problems that we're solving is this problem of precision agriculture. And we think that these kind of biosensors are the solution to that. Now, what I'm going to do is I'm going to say thank you. I spoke quickly. I'm glad the video is going to be up on the sort of YouTube later on, so you can rewind it and rewatch it a few times. And if you watch it, if you go back and rewatch it, when you watch Solrun's experiment, you'll see the voltage changing. It was an experiment she was doing in real time, and you'll understand that that was the data I showed you later on as well. So what I'll do is I'm going to talk to my good friend Ali now and say, Ali, we haven't had many questions, and maybe we didn't explain to people that we should have asked them to put questions in the chat box. But I just want you to kind of give me some reflections, Ali, from your perspective as well, if you don't mind, and maybe some comments in Persian as well would be good.
Yeah. دوستان اگه کسی سوالی چیزی داره میتونه توی همون چت باکس بذاره. اونایی که حالا جوین شدن ظاهرا به یوتیوب شما انتقال داده شدید، میتونید سوالاتتون رو تو همون چت باکس یوتیوب بذارید. آقای مارتین نگاه میکنن و جواب میدن. آقای دکتر چند نفر شما میبینید الان تو یوتیوب؟ شما میتونید ببینید؟
Just my interest, Ali. I mean, you're quite interested in water quality. What are your thoughts about, you know, measuring nitrate in water? Because we're doing it for soil, but of course, you know, I feel like, you know, it could equally be applicable to soil and to water as well. What are your thoughts on that?
Well, I think that's a good idea if we can use the same platform for monitoring nitrate concentration in water. But as you know, one of the problems in online monitoring is the regeneration of the surface of the electrode. So actually, I was trying to ask you that how do you manage the regeneration of the surface of the electrode in order to not lose the sensitivity? Because as you know, if the surface is getting saturated by the analyte, it's very likely you lose some sensitivity over the time.
Yeah,
and this is a common problem in all online monitoring systems.
Yeah, I think it's a good question. I mean, essentially, I mean, with these ion selective electrodes, you need, you know, you have a hole in them that's meant to take the anion, and so in order not to get saturation, you need to have more pores than you have anions. So there will be a point at which we will no longer be responsive to the amount of nitrate. But we haven't reached that saturation at the moment. So at the moment, we've just, you know, I think it's fair to say that we're kind of playing in the 20 ppm region, and we're going up to like 40 ppm. And the reason, so we've tuned the sensor to work at the concentrations that people essentially think are in the soil. But you are correct that there must be a point at which we can't put any more nitrate in there because it becomes saturated. So I wouldn't say we have solved it. We've just, I think we've just optimized it for the actual concentrations that we think we're going to be doing. And I think that's an important part of practical biosensing development, that you're always compromising and optimizing. You're not making the world's best sensor. If I want the world's best result, I'll give it to you, and you'll take it in the lab, and you'll make a perfect measurement on it. But when you're making real-time sensors, you have to accept, you know, imperfection.
Yeah. So now, what is the maintenance interval for the developed sensor in soil for soil application?
So the maintenance at the moment we've got, in this data I'm showing about 3 months worth of continuous data. So that tells us that we can put the sensor in the soil, leave it there for 3 months. Now, we'd ideally like to, the next milestone is 6 months and then 12 months. But I'm really not expecting these sensors to last more than 12 months. I feel like, it's, I don't want to say impossible, but it's getting pretty close to being impossible. So the maintenance in the end is once a year, they will have to be replaced. We will have to take the rods out of the ground, put new sensors onto them, and put the rods back in the ground. So that is some people would just say, well, I want it to last me 5 years. And that's fine, but we're going to have to wait 20 years until we've really made that robust enough to last that long. And just to make everyone laugh a bit, when you make sensors for the soil, the biggest problem is not the sensors, it's things like the deer coming up and chewing on the sensors. So it's all the things that you didn't expect to take place that are taking place. So you find yourself maintaining these devices, not because the sensor went bad, but because a deer thought that your cable looked very chewy, and the deer decided to chew through the cable. So this is just a quick comment, actually. If you're developing a biosensor and you want to commercialize it, get it into the field as quickly as you can, because you're going to find out the real problems as opposed to the problems that you imagine. And then you find out that actually it's vermin and rodents are the bigger problem rather than the sensors themselves. But yeah.
And what about the calibration? Do you need any calibration before you replace the sensor?
So what we do is, at the moment we're using average calibration factors, but we both know that that's it can be a bit risky. So what we do is we do a single point calibration. So when we put the sensor into the soil, we take a soil sample, we analyze it in the lab, and that tells us on day one, the nitrate was definitely this point. Now you can understand, Ali, the sensors can start drifting. So we do accept that, but they're most accurate when we first put them in, because we do a 1 point calibration and then they drift. What you will be quite interested about, though, is when you look at the data that the guys were doing in the lab, it was only a few seconds, but it was really flat. So the sensors are quite stable, but we're most accurate on day one, because that's when we do a single point calibration. And after 12 months, I think the trends will be correct, but the absolute accuracy won't be so correct. But the trending should be okay.
Yeah, I agree with you. But if you are looking for accurate concentration of nitrate, then you might be needing some calibration in between.
Yeah, we agree.
So I think this.
Sorry, Ali, go ahead.
So I think this technology can be adjusted for water monitoring application, because you have already developed the system. All you need is to just change the format. So this is this with my colleague, and I think this is one of the areas we need to talk with you in future. And if you want to start something with you, I would say this is the first thing we can start with.
Perfect. So what I want to say is this. Now, unfortunately, I do have a hard stop in a few minutes. But what I want to say is I want to say thank you to Shiraz and for you for giving us the opportunity to speak. I also want to say if there's undergraduates or graduates who are interested in doing projects with us, then they should, contact us or contact the University of Shiraz and say, would you like to do a project with us? We'll be quite happy to try and support people. You can find us through the Developer Zone. Find us on LinkedIn. It's quite a good place to find us. Find us through Ali. But, if you can find us then and you would like to do a project with us, then please, reach out to us and we will try and support you in your academic studies.
So, okay, Martin, thank you. So do you want me say the same in Persian?
Yes,
or
good point.
That's
Thank
enough, you think?
Yeah, please do.
دوستان مارتین گفتن که اگه کسی دوست داره از کسایی که فوق لیسانس دارن یا دکترا دارن، اگه کسی مایل هست بخواد حالا برای فوق لیسانس یا دکترا ادامه تحصیل بده، شرکت زیمر پیکاک این فرصت ها همکاری دارن و این شرایط وجود داره که حالا به صورت پروژه مشترک بین این شرکت و حالا دانشگاهی که باشون کار میکنن انجام بشه. حالا اگه کسی مایل بود بخواد پروژه‌ای رو با شرکت زیمر پیکاک انجام بده، حالا میتونید به من بگید، میتونید به آقای دکتر همتی نژاد توی دانشگاه شیراز بگید. فکر کنم به خود دکتر بگید بهتر باشه. حالا بعد حالا ما هماهنگی لازم رو میکنیم که ببینیم به چه صورت میشه انجام داد. و اینکه مرسی از کسایی که تشریف آوردن، انشالله که مفید واقع شده باشه و استفاده کرده باشید. And I would like to say thank you to you, Martin, for accepting Iran. And I am really happy to be in this webinar today because every time I go on a webinar and you are there, I really learn so many things.
No,
so thank you.
No, thank you very much. I've learned so much from our sort of interactions over the last sort of at least last year that I appreciate your interactions with us. And I would say I've definitely learned a lot back. So I do appreciate our interactions and our collaboration. So thank you.
Yeah, and I would like to say a big thank you to Dr. Yamini, who really helped us to organize this webinar. And also thank you, Dr. Hemati Nejad. I think he is disconnected, but he will be seeing the recorded webinar in future. So thank you to Dr. Yamini and thank you to Dr. Bahram-Nejad.
Thank you very much. And hopefully people will contact us soon. Thank you, Ali. And